All right, this is section 8.1, Basic Integration Rules. Before we start that, I want to tell you a little bit about this chapter. We're going to be talking about different techniques of integration and learn how to integrate some things you haven't been able to before now. And we're also going to talk about something called an improper integral. Before we start this, I want to remind you of some integration techniques that you already know. Sometimes I can spell. Integration techniques that you already know from Calculus 1. And we reviewed a few of those already in this unit that we just finished. So here's some things that I'd like for you to recall about integration. First, you've probably heard me say this more than once already in this course, is you want to simplify first. Simplify the integrand first. What I mean by that is do any algebraic manipulation that will make solving for the antiderivative much easier. For example, if I gave you this indefinite integral, and you decided you wanted to split this into two integrals, the integral of sine squared of 5x dx plus the integral of cosine squared 5x dx, you can actually, that can be done, but it's a lot of work and it's really hard. But if you realize that you have a Pythagorean identity in place there, the sine squared of any angle plus cosine squared of that same angle is always 1. By simplifying first, you've made this a very easy antiderivative. Right? And that's just a very quick example, but like if you had a product of two binomials, you would do that first and then integrate the resulting polynomial. So to give these some bullet points here, you might want to rewrite the integrand, the function that's being integrated is called the integrand. Which might be to rewrite, you might do something like multiply by a form of 1. And we'll see examples of all these. We might need to split a fraction into two parts, or three or more, whatever it takes. And what I mean by that is if you have something that looks like this, you can split that as needed into each term in the numerator over the common denominator with additions and subtractions in between as needed. Another way that we rewrite the integrand is to take radicals and rewrite them as powers, such as the square root of something is that something raised to the 1/2. Or having a monomial power of x in the denominator like this, that you'd want to rewrite that as a power of x. So this one, for example, would be x to the -2. Or you might add a form of 0. And we'll see an example of this so that you understand what I mean by a form of 0. And then another thing that we've talked about before in Calculus 1 is the U substitution techniques that we should be able to still use. All right, so those are the basics. Walking into this class, you should already know most of this and be able to do it without any problem. Now we're going to work on things that you don't know how to do. So if you look at the table that I've copied there from page 516 in your textbook, these are all of the basic integration rules. These I'll refer to as the basic 20. And these are the 20 that you should have memorized and know very well without my having to prompt you about them. You should know all these. Okay, so let's do example 1, part A. And you might look at A, B, and C and see how similar they are to each other. All that's changing is the power of x in the numerator. And I did that on purpose because I want you to see for rational functions what your possible procedures might be. Okay, the first thing you check is, well, is this one of our basic 20? And if we pull that 4 out, which of course we can pull the constant out according to rule number 1, and make this 4 times the integral of 1 over x squared plus 9 dx, then look through the first 20 and see if there's anything that reminds you of that. Well, if you look at number 19, I think we've got it. I know the a is supposed to be a constant and the u is a function of x, and this one's reversed from that, but since they're added, that doesn't matter. So it looks like the u squared in this problem is x squared, which means that u is x and du is dx. And since du and dx are the same, that means I do not need to introduce any new constant into the problem to be able to do this. So I think we're good on that count. And then a squared is 9, which means a is 3. And so according to number 19, this is going to be the constant that was out in front, 4, times 1 over a times the inverse tangent of, or arctangent of, u, which is x, over a, which is 3, plus c. Okay. So when you have a rational function, sometimes you're going to use something that's maybe related to one of our basic 20, like maybe 18, 19, or 20 might somehow come into play. Or maybe a u substitution or something would work. Okay, so now let's look at the next one, b. Looks a lot like the last one, but this time it's 4x over x squared plus 9 dx. Now, although we can pull the 4 out in front, which I am going to do, this one is not like the last one because we now have a variable x in the denominator that we did not have last time. And so it doesn't fit the pattern for number 19 because of that x. So the next thing we might try is, well, let's try u substitution. What if we let u equal the denominator in its entirety? That means that du is equal to 2x multiplied by dx. And do we have all of that? The essential part of that we have to have is the x and the dx. And that essential part is there. There's the x there's the dx. The thing that's missing is the 2, and this is what I was referring to earlier. When we didn't have to do something in the last problem. This one does need a 2. So I'm going to multiply by 2 because I need it. But I can't just multiply by 2. I can multiply by a form of 1. So I'm going to multiply by 2 as well as multiply by 1/2 outside in front of the integral. So in essence, all I've done is multiply by 1/2 times 2, which doesn't change the value, it just changes the look of what I'm dealing with. Okay, so out in front, 1/2 times 4, of course, is 2. The underlying 2 and x and dx become du. And the denominator is u. And the antiderivative of 1 over u, this is number 5, is 2 times the ln of the absolute value of, please don't forget the absolute value in this problem, of u plus c. Then going back to the original variable, that's 2 ln of the absolute value of x squared plus 9 plus c. Since x squared plus 9 can never be negative, in fact the smallest you could get for x squared plus 9 would be 9, the absolute value of any answer to that x squared plus 9 is going to be positive, and so the absolute value in this particular problem is superfluous, and I can take away the absolute value and use parentheses instead. Now of course you can't always do that. If that expression can be negative, the absolute value has to stay. But if what you know is inside, it will always, always, always be positive, or at least 0, as long as it's non-negative, the absolute value can be removed. Please don't do that unless you know for sure that you're not changing the potential values that we could use for x. Okay, c. Now we have 4x squared over x squared plus 9 dx. And the procedure here, for any rational function where the degree of the numerator, here it's 2, and the degree of the denominator, here it's 2, are the same, or if the degree in the denominator is greater than the degree of the denominator. So, like if I had 4x cubed over x squared plus 9, or 4x to the 17th over x squared plus 9, if that power of x in the numerator is greater than or equal to the power of the denominator, the way you do this type of problem is you rewrite the integrand by division. So we're going to go off to the side and do what's called a lemma. This is side work that's important, but we go off to the side to save ourselves from having the flow of our problem interrupted. So this is important side work for which we'll get an answer and come back to our problem with a result. So this side work is to do the division of x squared plus 9 divided into 4x squared. So what do you multiply x squared by, the first thing in front? What do you multiply it by that would give you the first thing under the division symbol? What would you multiply x squared by to get 4x squared? Well, the answer, of course, is 4. Then multiply 4 times x squared plus 9, so that's 4x squared plus 36. And of course, behind the 4x squared above, I could put in a plus 0 without changing what I had there to begin with. And then once you've done that multiplication, the next thing to do is to subtract. 4x squared minus 4x squared is 0, x squared, and I'm not going to write that. Then 0 minus 36 leaves negative 36. X squared does not go into negative 36, so we're going to stop the problem and say that this division has now been done, and 4x squared divided by x squared plus 9 gives us a quotient of 4 plus, then we take the remaining part, the remainder, negative 36, over the divisor x squared plus 9. So, going back to our original problem from that lemma, we're going to take from that we get 4 minus 36 over x squared plus 9 dx. Then we can split that into two integrals using number 2 in the list of 20 and do the integral of 4 dx, which is 4x, minus 36 times this integral. I just pulled the 36 on out in front. And lucky for us, we did the integral of 1 over x squared plus 9 dx a few minutes ago. So I'm going to roll back and pick up our answer from what we did earlier. Be careful. Ignore the 4 in problem A. We're looking for the answer for the integral part. So we're looking for the integral here. Its answer is that. So that's what we're going to pull down below. Okay, so that's 1/3 tangent inverse of excuse me, x over 3 plus c. And then simplifying our answer, we get 4x minus 12, arctangent of, or inverse tangent of, x over 3 plus c. So those three show you that even though they all are rational functions, because of the form they're in, they can have very different looking answers. And notice part C actually used one of our earlier answers to continue to the final answer for part C. So, excuse me, something interesting there. All right. So let's turn to example 2, and we're going to find a bunch of integrals here. Example 2. Let's start with part A. A definite integral from 0 to 1 of x plus 6 over the square root of 9 minus x squared. And what I'm going to suggest that you do is, as soon as we've written this first one down, I'd like for you to pause the recording and think about it and see if you can come up with how to integrate it all by yourself before you listen to my explanation. I think that'll really help you. Okay? So think about that. All right. So what I thought of doing here was splitting the fraction. One of the things I mentioned as a possibility at the outset. I'm going to split this into x over the square root of 9 minus x squared plus 6 over the square root of 9 minus x squared. Dx. Now, for the first part of this, I'm going to think of that as its own integral. I'm not going to write necessarily two separate integrals for this. I'm just going to think of them as separate things. For the first one, I'm going to let u equal 9 minus x squared, the thing under the radical, which means du is negative 2x dx. So actually, I sort of misspoke. I am going to write them separate here. So this will become 0 to 1 x over the square root of 9 minus x squared dx plus the integral from 0 to 1 of 6 over the square root of 9 minus x squared. Because I decided this first time I didn't want to leave out very many steps and have you wondering how I got from here to there. Okay, so that's just the splitting of the two. And the thought process I already went through is good. I'm not going to take that back. It was fine. So for the first one, using u substitution, I need for my du to be negative 2 times x times dx. The essential part of that is x dx. And so I have that. The only thing I'm missing is that negative 2. So I'm going to introduce that negative 2 by multiplying inside by negative 2 and outside by negative 1/2. Notice this is why I needed to split, because the second integral doesn't need that negative 2, nor would it have a negative 1/2 out in front. So what I'm going to do here is I'm going to continue working on the left-hand side and of this problem, and I'll come back and do the second part, the second integral of this in just a minute. Okay, so this is negative 1/2, and the negative 2x dx becomes my du, and this will be the square root of u. Now, since this is now a du integral, the upper and lower bounds of this definite integral have to be values of u. So I'm going to go back up here and talk about, well, if the lower bound is x equals 0, what is the corresponding value of u when x is 0? And the equation I'm going to use for that is my u substitution equation. So if x is 0, 9 minus 0 squared is 9. So the lower bound for the first integral will become 9 with that u substitution. The upper bound, 1, when x is 1. What's the corresponding value of u? 9 minus 1 squared is 8. So the upper bound is 8. Okay. Then to do this integration, I'm going to rewrite that radical as a power, and since it's in the denominator as well, that's going to become u to the negative 1/2 du. And the antiderivative of u to the negative 1/2 is u to the 1/2, because I've added 1 to negative 1/2, divided by the new power 1/2, evaluated from 9 to 8, which simplifies to be negative square root of u, because the 1/2s cancel, from 9 to 8. So by substitution, that's going to be negative square root of 8 minus negative square root of 9, which is negative 2 square roots of 2 plus 3. All right. Now that's that part done. Now we're going back to the second half. And by the way, splitting this into two separate problems and adding the results, I very well could finish one half of this way faster than I finished the other half. So I may be carrying down answers in this if I do the second half much faster than the first half and just carry those answers down. So you'll see that. I think that's what's going to happen here. Anyway, to do this integration, look at the list of basic 20 integrals that I gave you earlier to look at. And I can't remember them by number, so I'm looking this one up by number. This one is, if we pull that 6 out, let's go ahead and do that first. Pull that 6 out. Is there one of those basic 20 that you see could be used here? Yes, it's number 18. So for number 18, I need to identify what u squared is. That's going to be x squared, which means u is x, du is dx. So I don't need to introduce any new constants there, like I did for the other half where I had to introduce that -2. My a squared, of course, is 9, which means a is 3. And so the antiderivative of that is the 6 that we pulled out times, for number 18, arc sine, notice there's no 1 over a there, arc sine, or sine inverse of u, which is x, over a, which is 3. And that one is evaluated from 0 to 1. We never went out of x here. Our formula let us stay in x the whole time, so I did not have to change the bounds. So this will be 6 arc sine of 1 over 3 minus 6 arc sine of 0 over 3. Okay. 6 times sine inverse of 1/3. Is 1/3 one of the special answers you saw in pre-calculus when you took the sine of some nice reference angle? Did you ever get 1/3? Well, the answer is no. So this is the best we can do for an exact answer. If we'd gotten 0 here instead of 1/3, or 1/2, or square root of 2 over 2, or square root of 3 over 2, or 1, or opposite of one of those numbers, then we could actually find an exact answer for this inverse sine, but we can't here. Sine inverse of what will simplify to be 0 is 0, so 6 times 0 is 0. And like I said, we finished this half a little bit sooner than we did the other. I tried to draw it out a little bit to see if maybe I could make a match, but no such luck. So I'm going to get to copy that twice. Oh well, that's okay. And that is a final answer. All right, so that was part A. Let's do part B. So this is the integral of x cubed over the square root of 25 minus x to the 8th dx. So pause the recording and see what you can think of to do this problem, and then come back and see how close you were. Okay, I'm going to ignore that x cubed for just a second and look at the list of the basic 20. Again, I don't have these memorized by number, so you have to look at it. This is 18 again, isn't it? Maybe. That x cubed may get in the way, but let's see. If we're going to treat this as number 18, that means that our u squared is x to the 8th. So that means that u is x to the 4th, and du is 4x cubed multiplied by dx. Well, actually, that x cubed is essential to go forward with this. I need the x cubed and the dx, which I have, and what I'm missing is that 4. So I'm going to introduce that 4 while at the same time multiplying by 1/4, so that in essence all I've done is multiply the problem by a form of 1. Okay. In this problem also, the a squared is 25, which means that a is 5. So our answer will be 1/4, which we get from the front of the last integral, multiplied by, according to number 18, arc sine, notice again there's no 1 over a here, arc sine of u, which is x to the fourth, whoops, wrote 3, x to the fourth, over a, u over a, plus c. Okay, part C. 1 over 1 plus e to the x dx. So spend a few minutes and pause the recording and spend a few minutes seeing if you can figure out how to integrate this one. Okay, well, I thought of several different things and ended up discarding a few of them because they didn't work. You may have done the same thing. I tried to let u equal e to the x, didn't work. I tried to let u equal 1 plus e to the x, didn't work. And in fact, in this problem, one of the ways we could attack this one is to add 0. And having tried some of the u substitution ideas that I had before, this is what made me think of this. I'm going to add a form of 0 to that numerator, and the form of 0 is going to be e to the x minus e to the x. Nice form of 0 there. So if I split that fraction into two fractions and make it 1 plus e to the x over 1 plus e to the x minus e to the x over 1 plus e to the x dx. I think we can do that problem because the first fraction simplifies to be 1. Now, I don't know if you tried this early on in your process with this one, but if I let u equal 1 plus e to the x, the denominator thing, then du is 0 plus e to the x, coolest function ever, times dx, which in the second fraction there, I have the e to the x and I have the dx. Okay, so I'm good to go. So integrating the first part, the integral of 1 dx, of course, is just plain old x, minus the integral of 1 over u, that's 1 over 1 plus e to the x, times du, where du is the e to the x times d to the x kind of absorbed together into that du. Okay, so x minus the integral of 1 over u du is natural log of the absolute value of u plus c. And then going back to our original variable, that'll be x minus the ln of the absolute value of 1 plus e to the x. And again, 1 plus e to the x is always non-negative, so the inclusion of those absolute values is actually a superfluous thing. I can take them away. And by the way, if you decide to leave them, that's not a big error. The big error is taking them away when you're not supposed to. Leaving them when you could have taken them away is a lot less egregious of a mistake. So I would rather you err on the side of don't take them away unless you're absolutely certain that you can. The next example is part D. So let's take a look at that one. D is the integral of cotangent of x multiplied by the ln of sine of x. dx. Okay, so pause the recording and see what you can come up with all by yourself. This is what I thought of. If I let u equal the ln of sine of x, this may not have been the first thing I thought of, by the way. I could have tried other things that failed, but this is the thing that ended up working for me. Then the derivative of that, the derivative of natural log of something, is 1 over that something times the derivative of that something. The derivative of sine of x is cosine of x times dx, which means that du simplifies to be cosine over sine, which is cotangent x, dx, which is exactly what I have here and here already. And so by substitution, everything I didn't underline is u, and everything I did underline is du. And the antiderivative of u to the first is u to raise power by 1 to 2 and divide by the new power. So 1/2 u squared plus c. Then going back to the original variable, this will be 1/2 times the natural log of the sine of x squared plus c. All right. So let's look at E. This is the integral of tangent of 2x quantity squared dx. Okay, I'll give you a minute to look at this one, and so put me on pause and then come back when you've got an answer or some attempts that did not work. Okay, for this one, if you look at the basic 20, this is actually one of them you're supposed to know. Well, actually not directly. Let me back up from that just a second. And I was jumping ahead of myself because in my head I was further along. The first thing I notice is that I have the tangent of something. And so one thing I can do is let u equal 2x, which means du is 2 times dx. Of course, I have the dx already. I'm missing the 2. So I'm going to multiply inside by 2. So I have that. But in order to do that, at the same time, I have to multiply outside by 1/2. Okay, so this is 1/2 of the integral of tangent squared u, and then dx and 2 become du. Well, to take this one further, you're going to have to remember an identity from pre-calculus, one of the Pythagorean identities, the one that has tangent squared in it. And if you solve that identity for tangent squared, you end up getting secant squared. Oops. Sorry about that. Secant squared of u minus 1. And you'll hear me say this probably several times during this course, but everything you've ever learned from a prior course, you get to see it again at some point or another in this course. So that trig identity is a good example. Okay, well, if we split that integral into 2 and distribute the 1/2, well, I guess we're distributing the du as well. 1 times du is just du. That's what we'll get. And secant squared u, this is where I was going earlier, is one of our basic 20. It's number 14. And the antiderivative of secant squared u is tangent of u. And the antiderivative of 1 du is u. Hopefully you did not say x accidentally. That would be bad. It's u. And then taking it back to our original variable, that'll be 1/2 tangent of 2x minus 1/2 times 2x plus c. And so our final answer is 1/2 tangent of 2x minus x plus c. All right, so we got to see several different example integrals and did a few of the things that I mentioned that might occur. So in this section, you're going to be reviewing some things that you learned in Cal 1 and expanding that just a bit by using some of these rewriting techniques. Look at the table on the last slide. You can do some algebraic manipulation, like if you have a binomial squared, you can do that squaring, or multiply the two binomials or whatever, and then integrate the result. You can separate the numerator, which we did that a couple of times. We can complete the square, which we didn't mention this time, but notice that x squared and 2x in that problem, you would want to complete the square on that in order to get that form, which would be one of your basic 20 after all. You can actually do the long division, and we did an example like that one. You can add a form of 0, like they added 2 minus 2 to that problem, and split that into 2 fractions. You can use a trig identity. We saw that with the last one, tangent squared, being replaced by secant squared u minus 1. And you can, especially if you have 1 plus or minus a trig function in one part of the fraction, like 1 over 1 plus sine of x, you can multiply that by a form of 1, its conjugate over itself. The conjugate of 1 plus sine x is 1 minus sine x, and so that over itself is a form of 1. 1 minus sine squared in the denominator, using the trig identity, becomes cosine squared, and then split that fraction, and you can integrate secant squared x and minus sine x over cosine squared x. You can use u substitution where u is cosine x to do that one. So these are some examples of things to look for in this section. You're going to have to be persistent, keep trying, and if it doesn't work, the first thing you try something else, and try something else, until finally maybe you stumble upon the correct thing. So that ends this lesson for today. I will see you in class.